Hello everyone. So our problem is 575. Member AB is supported by a cable BC and at A by a square rod which fits loosely through the square hole at the end joint of the member as shown. Determine the components of reaction at A and the tension in the cable needed to hold the 800 Newton cylinder in equilibrium. So we are given a rod, okay, and this is an L-shaped rod as you see, and there is a square rod which is fitted loosely at point A. Now this L-shaped rod is pulled by a cable from point B and it is fixed to the wall at point C. Now, first thing that we have to do is to analyze the joints. And in fact, I will analyze beginning from the B. When I look at the B, we know that cables cannot carry compressive load. So when you compress it, it will be somehow bended, curled, or it will not carry any load if you put a weight on it. But certainly they can carry tension. So you can pull them. So this means that there will be a force from B to C which acts on the L-shaped rod, and it will be in this direction on the L-shaped rod. So this basically means that the force on the cable is reversed, and that is tension. Okay, so this is what we have at point B. Now let's focus on point A, and let's isolate it from the rest of the problem. So I will focus on point A. First, I will look at the translational motion. So what is a translation? So basically, if you move your hand from here to here, as you see, it moves to my left-hand side from my right-hand side. So that's a translational motion. Now, let's see. First, I will look at the X, in X direction. Now, certainly, in X direction, this joint can freely move because the connection is loose. As you see, so since the connection is loose, it can easily move. Okay, this is one thing. How about the other directions? For example, Y direction. Can the joint A move in Y direction? No, it is prohibited because the joint A cannot move, restricts the motion in Y direction. Identically, the motion in Z direction is also restricted. This basically means that at joint A, there is a force component in Y coordinate which restricts the motion, and there is a force component in Z direction which restricts the motion, but certainly there is no force component, reaction force, at joint A in X direction. Okay, now how about the rotation? Again, I will isolate the joint A from the rest of the structure. Now I will look at the rotation. So around which axis can the joint A rotate? So first I will look at the x-axis. Can it rotate around the x-axis? No, it cannot rotate because because the rod inside is square and the shape will avoid the rotation. If it is a circular rod at the junction, at the joint A, certainly it can easily rotate around x-axis. But in this case, it's not. It basically means that there is a moment which restricts the rotation. Okay, so we have a moment component, reaction moment, in x direction. We can say that. For the moment, I say that, I say that I have a moment in x direction. How about the y-axis? Can the joint A rotate around y-axis? No, it cannot. This basically means that there is a reaction moment in y direction. It is the same for the z-axis because the joint A cannot rotate around z-axis. As a result, we have a component of the moment in z direction. Now these are the things that that we see when we analyze the problem. Okay, now let's begin by drawing the free body diagram of the problem. Always draw the free body diagram. Always. Here is my free body diagram. So I don't need to draw everything. It is just a schematic which shows the loads acting on the structure. Certainly, I have a weight here, W. I have a tension force at point B coming from the cable. Certainly, I say that this joint, this junction, the corner is labeled as D. I give a label there in order to simplify the things. And at point A, I have a reaction force and the moment, reaction moment. Of course, first thing that I need to do is to write the position vectors. In this problem, we are given the coordinate system, so we don't need to define a coordinate system. I will define all the position vectors with respect to this coordinate system. In fact, point A is at the origin of the coordinate. As a result, position vector of A is 0. Now point B, it is minus 0.3 I vector plus 0.6 J vector. Now next thing is RC. So the position vector of point C, because I need to determine the direction of the tension coming from the tensile force coming from the cable. It is 0.2 K vector, and D, where the weight is hanged, it is 0.6 J vector. Okay, how about the force FA? I have FAXI. So remember that I already said that FAX is 0, but for the moment, I will leave it in my expressions. FAX I vector plus FAY J vector plus FAZ K vector. Next thing is the moment at joint A, reaction moment, MA. I have MAX I vector plus MAY J vector plus MAZ K vector. Weight It is in negative z direction. Certainly it is given to us. It is minus 800 k vector. And the tensile force coming from the cable, it is the magnitude. We know the direction, UBC. Well, we don't know it yet, but we can calculate it. So T multiplied by UBC. So T is a scalar quantity. Okay. Now, first thing that I need to do is, next thing is to calculate the unit vector from B to C, UBC. So this is the relative position of C, point C with respect to B, RBC, divided by magnitude of the vector. This will give me the unit vector UBC. So in fact, relative position of point B with respect to C is RC minus RB. That's okay. If I do calculation, what I'm going to get is 0.3 I vector minus 0.6 J vector plus 0.2 K vector. And indeed, the magnitude of this vector is 0.7. If I divide this expression, this vector with its magnitude, I will obtain the unit vector. And what I'm going to get is 0.428 I vector minus 0.857 J vector plus 0.285 K vector. Now, I define the unit vector UBC. Next thing is to write the equilibrium equations. We know that sum of the forces in all directions has to be equal to 0. This is our first condition for static equilibrium. So in x direction, I have Fax and x component of the tension. Certainly, x component of the unit vector is 0.428. Therefore, I have Fax plus 0.428 T I vector. Next, I have Fay. So this is my summation in x direction. So I sum up the y components of the forces. I have Fay. Then y component of the tensile force coming from the cable, it is minus 0.857 T plus minus 800 plus Faz plus 0.285 T vector, T K vector. And this has to be equal to 0 as well. Now, in order this vector to be 0, the coefficients of I, J, and K has to be equal to 0. Now, let's begin from the x component. So remember that Fax is equal to 0. Because the joint A can freely move in x direction without having any restriction. This basically means that tension T is equal to 0. Okay, now I know tension is 0. So let's look at the y component. So this term vanishes. This means that Fay is equal to 0 as well. Oh, sorry. Now T, it has to be equal to 0. Okay, so fay is equal to 0. That is something. Now let's continue further and look at the z component. So remember that tension is 0. This means that this term vanishes. Now from here I can easily say that faz, because in order the expression inside the parentheses to be 0, faz has to be equal to 800. Okay, so these are the findings. So let's write it. In fact, fax is equal to 0, fay is equal to 0, and faz is equal to 800 newtons. Okay, now we have found the forces, reaction forces at point A, but how about the moments? Of course, we have the second equilibrium condition. Now, second equilibrium condition tells us that the sum of the moments in each direction has to be equal to 0. Now, let us write the moment then with respect to origin. We can take the moment with respect to any point, but certainly the most logical choice is the origin in this case. So array multiply vector product fa. So this is the moment generated by fa, plus rd vector product w. This is the moment generated by the weight. rb multiplied by tension. This is the moment generated by the tensile force coming from the cable, plus reaction force at the junction A. So if we do the operations, what we are going to get is MA plus 0.171 T minus 480 I vector plus MAY plus 0. So just corrected, there is an extra 0 here. 0.857 T. Sorry, just let me check it. Maybe this is not the case. This is RB multiplied by T. Let's check the RB. (0.3 I vector, 0.6 J vector, and from I to J components will not form. J to K will give us. So I to K will give the J 0.3 multiplied by 0. Okay, so I will clear everything. So the Y component of the force is MAY plus 0.0857 T vector. So this is correct. Plus MAZ K vector, and this has to be equal to 0. Now let's look at the components. So this has to be equal to 0. This means that the coefficients, or in other words, expressions inside the parentheses, has to be equal to 0. Now, This automatically tells us something. MAZ is equal to 0. Okay. Now remember that tension is equal to 0. This means that MAY is equal to 0 as well. Now, if I go to this expression, remember that tension in the cable is equal to 0, so this term vanishes. And from here, I can easily say that MAX is equal to 480 Newton meters. So as a result, MAZ is equal to 0. So Z component of the moment, reaction moment at joint A is equal to 0. MAY is equal to 0. So Y component of the moment at point A is equal to 0. But X component of the moment is 480 Newton meters. So X component of the force at point A is equal to 0. Y component of the force at point A is equal to 0. And Z component of the force is equal to 800 newtons. Certainly, the tension in the cable is also 0, is equal to 0.